I now want to start to look at how we can use the quotient group to kind of factor out these unwanted properties. And I'm going to start by looking at factoring out elements of finite order. Let's let G be some abelian group, and we're going to let H consist of all of the elements of G that have a finite order. Every subgroup of an abelian group is normal, so we know that H is normal. And this comes from the fact that if we have XH, X inverse, abelian says we can switch the order. So it's just equal to little h, which is definitely still in my subgroup. So this is definitely a normal subgroup. That means we can form the quotient group. In addition, if I look at the quotient group GH, then it actually has no elements of finite order with the exception of the identity element. So let's go ahead and show that this is true. Let's suppose that this quotient group does have an element hx of finite order. This means that there is an integer m not equal to 0, such that hx to the m power is equal to h, since h is the identity element of G mod h. Well, by definition of coset multiplication, this is h x m. That must be equal to h. We showed in the previous video that if a coset is equal to h, since hxm is equal to h, I've shown in a previous video that that implies that x to the m power is in h. Since h is all of the elements of finite order, that means x to the m must have finite order. So let's suppose the order of x to the m is t. Then we would have xm to the t power, which is the same thing as xmt, must be equal to the identity. So then x must have finite order since I have x to a finite power is equal to the identity. So that means x must belong to my subgroup H, which tells me that hx is equal to h, and we said the only element that has finite order is the identity. So I've proven that if we have an element of finite order, it must be the identity. Let's do a quick summary of what I just showed. Let's let H be a subgroup of G, which consists of all of the elements of G that have finite order. Then this G mod H has no element except this neutral element that has finite order. In a sense, I've factored out all of the elements of finite order. I put them all in H, all of this identity element. So now I have a quotient group whose elements all have infinite order, once again with the exception of the neutral element. So if I have some group G, a commutator is an element of the form A, B, A inverse, B inverse, where A and B are both elements of G. In an abelian group, all commutators are equal to the neutral element. They're all just the identity, since I could rearrange the order and cancel things. In a general group, the fewer and fewer commutators we have, the closer and closer the group is to being abelian. So let's let H be the subgroup containing all of the commutators of G. So if I have some group G, let's let H be the subgroup consisting of all of the commutators of G. I would technically need to prove that this is both a subgroup and a normal subgroup. I'm not going to do that here. Instead, I'm going to take advantage of the fact that this is a normal subgroup of any given group G. So I want to look at G mod H. And in fact, I'm going to claim that G mod H is abelian. If I can factor out all of the commutators, I get an abelian group. So what I need to show is that HX-HY is equal to HY-HX. Or, equivalently, HXY is equal to HYX. Well, I've already shown in a previous video that HXY equal to HYX is true if and only if xy, yx inverse belongs to H. So what I showed was H of A is equal to H of B if and only if AB inverse is in H. So the A is xy, the B is yx, and so I have that. Rewriting this, I have xy, x inverse, y inverse. Whenever I distribute the inverse, I need to switch the order. Belongs to H. And this thing here is just a commutator. And it is, in fact, a commutator. So if H has all of the commutators, then we have that G mod H is abelian.